Okay, in this section, we're going to see another family of identities that are very useful and that emerge almost directly from the sum and difference identities of the last few sections. So these are called double angle identities. So let's first motivate these double angle identities, and then we'll use them in a few examples. So make the following observation. Cosine of 2a, and this is the form of a double angle because it's 2 times the angle. Well, we know that this is equal to cosine of a plus a. That's what 2a means. And writing it this way, we can see that we should use the cosine, cosine, sine, sine identity here. So we're going to get cosine, cosine, and then the plus becomes a minus, sine, sine. And here, both angles are a, so it's just a is all the way down the line. All right, well, of course, cosine of a times cosine of a is cosine squared of a, and sine of a times sine of a is, of course, sine squared of a. So we have this identity here, which is the principal double angle identity for cosine. Okay, so while this is typically good enough, we actually are very close to 2 more forms of a double angle identity for cosine. So let's just kind of push the envelope a little bit here. Note that we can replace cosine squared with 1 minus sine squared. Of course, cosine squared is 1 minus sine squared by the Pythagorean identity that we know and love. So what would that get us here? That would get us, well, instead of cosine squared, we'll have 1 minus sine squared. And then we have another minus sine squared from this term. So we get cosine of 2a is 1 minus 2 sine squared a. And this too is regarded as a double angle identity for cosine. So this is cosine of 2a written in terms of sine. We could return to this principal double angle identity for cosine, and instead of replacing cosine squared with 1 minus sine squared, we could sort of equivalently replace sine squared with 1 minus cosine squared. See what happens in that situation. Okay, so sine squared is now being replaced by 1 minus cosine squared. And so if we distribute the negative on the right-hand side, we'll get minus 1 and then plus cosine squared a. And we can combine like terms on the right, so we get cosine of 2a is equal to 2 times cosine squared of a minus 1. All right. So these 3 are considered the 3 double angle identities for cosine. That first one is regarded as the principal one, of course, like I said. If you understand that one, then you can easily produce the other 2 as needed because you are, of course, familiar with the Pythagorean identity. So in my personal experience working with trigonometric identities, that first one is far and away the most common one that I call on when I need a double angle identity for cosine. All right, well, let's see if we can find a double angle identity for sine. So sine of 2a, we will uncover it the same way by writing 2a as a plus a. And now we'll unwrap this using the sine, cosine, cosine, sine identity. So that's sine, cosine, and then here the plus stays a plus, cosine, sine. Okay, so these are like terms. It doesn't matter that their factors are written in different orders. These are like terms, so we can combine them. So it's like this is a dump truck plus a dump truck is 2 times a dump truck. So this is 2 sine a, cosine a, and There we are. This is the one and only double angle identity for sine. And it too is eminently useful. And finally, let's uncover one for tangent. And we'll use the same tactic, writing 2a as a plus a, which will allow us to unwrap this particular form using the sum difference identity. And the one for tangent, of course, is tan over 1 tan. Tan over 1 tan. So again, all the angles here are a, which makes it a lot easier to reduce. So we have tan a plus tan a. Well, that would be 2 times tangent of a over 1 minus tangent of a times tangent of a, tangent squared a. And that is the double angle identity for tangent. All right, so let's put them all together here. So these are the 3 cosine double angle identities. There's the single double angle identity for sine, and there's the single double identity for tangent. So, okay, good. Let's look at some examples where we need to use these. All right, yeah, cool. One of these ones again. So we're given like a trig function and some vague information and told to find some other trig functions. And yeah, these are all kind of turning out the same. We need to use some sort of identity to connect what we're after with what we're given and then work everything out. So the first thing we should probably do is determine the quadrant of the angle theta. So we can see that from the given information, sine of theta is positive, so that narrows us down to quadrant 1 or 2, but cosine of theta is negative, so that rules out quadrant 1, which means that theta must be in quadrant 2. That's the only quadrant where sine of theta is positive and cosine of theta is negative. So keep in mind that we do not know the quadrant of the angle 2 theta. It's a completely different angle. And just because it's double a second quadrant angle does not mean that it's in the 4th quadrant. For example, speaking in degrees, 91 degrees is in quadrant 2, right? Just barely, 91 degrees. If you double it, you'll get 182 degrees, and that's barely in the 3rd quadrant. So, and at the other extreme, 179 degrees is also in the 2nd quadrant, just barely, and if you double that, you'll get 358 degrees, which is certainly in the 4th quadrant. So we don't know if 2 theta is in quadrant 3 or quadrant 4. Okay, so now let's find the pieces we need. So we need sine of 2 theta. Well, it's probably fair to assume that we're going to need the double angle identity for sine. Now, I really want to pause here and just remind you of how easily attainable these identities are if you ever forget them. As long as you know the sum and difference identities, which I know are kind of annoying to learn at the start, the ones with the chance, but once you've got those locked in, it will be very easy for you to recover all these other identities that we're going to see. So, for instance, let's say we weren't quite sure that this were the case, or we couldn't remember it at all, or we weren't maybe only 70% sure that this was true, but we're really solid with our sum and difference identities. Then, in a matter of seconds, you can recover. So by just reproving like we did, sine of theta plus theta, well, that would be sine, cosine, cosine, sine. And then, yes, of course, it is 2 sine theta cosine theta. So good. Now we have some conviction, and we're good to go. All right. So now this is what we're after, and this is what we need to work out. So we need to figure out what sine of theta is. Well, that's given. That's 3/10. And we do not know what cosine of theta is, but we can easily figure that out using classic techniques from the first few sections of this course. So we need cosine of theta. We'll just draw a triangle to get it. So we know that sine of theta is 3/10, so we'll label the opposite and the hypotenuse 3 and 10 respectively. And we'll use the Pythagorean theorem to find little b. So b is equal to the square root of 91. And therefore, cosine of theta, which is adjacent over hypotenuse, is going to be negative rad 91/10. And remember, cosine of theta is negative because theta was established to be in the second quadrant. In fact, they even told us directly that cosine of theta is negative. So now we have sine of theta and we have cosine of theta. We can determine what sine of 2 theta is. So sine of theta was given as 3/10, and cosine of theta was calculated as negative 91/10. So we can cancel a little bit here. 2/10 leaves us with a denominator of 5 there. So our denominator here will be 5 times 10, which is 50, and then we'll get negative 3 rad 91. So that's what sine of 2 theta is. Notice that it came out negative, which is what we would have expected because while we don't know the quadrant of 2 theta, we have it narrowed down to quadrant 3 or quadrant 4. And sine is negative in both of those, right? So this is conforming to what we would expect. Okay, the next thing we'll do is we will find cosine of 2 theta. And let's use this identity here. Cosine of 2 theta is cosine squared minus sine squared. Very good. Once again, you could easily recover that using the cosine, cosine, sine, sine, where all the angles are theta, so your cosine, cosine would be cosine squared, and your sine, sine would be sine squared. So very easy to recover. Do we have these ingredients? Well, yeah, we have cosine of theta. We worked it out right up there. And we were given sine of theta. So this one, not much work to do on this part. Okay, well, cosine of theta was negative rad 91/10. And that's being squared. And sine of theta was 3/10, and that's being squared. So the negative here is going to get squared away so that this will become a positive. Square root of 91 squared is, of course, 91 over 100 minus 9 over 100. And 91 minus 9 is 82 over 100. But this reduces to 41/50. So cosine of 2 theta is 41/50. We also can finally deduce the quadrant of 2 theta because sine of 2 theta was negative, of course, and cosine of 2 theta is positive. Well, that tells us that 2 theta must be in the 4th quadrant. It can't be in the 3rd because in the 3rd quadrant, cosine is still negative. The question didn't ask us for that quadrant, but it's fun to know. The last part of the question said, okay, find tangent of 2 theta. So we could use the tangent double angle identity, which is 2 tangent of theta over 1 minus tangent squared of theta. That would require us working out tangent of theta. Well, we already figured out sine of 2 theta and cosine of 2 theta. So honestly, the easiest way to get tangent of 2 theta, and I'm a fan of whatever the easiest way is to do something, is just to write tangent of 2 theta is sine of 2 theta over cosine of 2 theta. Sine of 2 theta is negative 3 rad 91 over 50. And cosine of 2 theta, we worked out to 41 over 50. So here we have a single fraction divided by a single fraction. We can write that as a multiplication by the reciprocal. And those 50s cancel because they're very nice. And we get negative 3 rad 91 over 41. And yeah, we could have predicted that this would be negative because by this point in the problem, we knew that 2 theta was in the 4th quadrant. So of course, tangent would be negative. Okay, so hooray, we're done. Okay, well this time we're given the double angle value, which is negative 12 over 13. And we're asked to find sine of theta. Okay, so we just need to think of an identity that relates cosine of 2 theta to sine of theta. Well, we know that cosine of 2 theta is cosine squared of theta minus sine squared of theta. So we could certainly use this identity because we're after sine of theta, and we know cosine of 2 theta, but we don't know cosine of theta, which we would need right here. So let's reach in and try to find a different cosine double angle identity, and maybe the one that doesn't involve a cosine, that only involves sines. Well, if you can't quite remember that one, you can easily just write cosine squared in terms of sines. So we'll write cosine squared is 1 minus sine squared. And then we've got that other minus sine squared. And then combining like terms, yes, this one. Okay. So there we are. We'll use this guy. So let's isolate sine squared. We can see that if we subtract 1 from both sides, we will get negative 2 sine squared theta. And dividing everything by negative 2 will give us negative 1/2 times cosine of 2 theta minus 1 is equal to sine squared theta. And in fact, if we distribute the negative into this binomial, we can swap the order of the 1 and the cosine, makes it a little bit nicer. So we have 1/2 1 minus cosine of 2 theta is equal to sine squared theta. This identity right here that we've just accidentally stumbled into is actually highly useful in calculus, as applying a calculus operation called integration to the square of the sine is not straightforward at all. On the other hand, applying integration to cosine to a first power is actually quite straightforward. So this identity, like I said, is used a lot in calculus. But that's not what we need it for right now, of course. All right, so let's just use the symmetric property of equality to write the sine on the left and this guy on the right. Okay, so we were given cosine of 2 theta. So let's plug that in and do our calculation. Cosine of 2 theta was given as negative 12 over 13. So therefore, sine squared theta is 1/2 1 minus negative 12 over 13. So this is like 1 plus 12 over 13, which we will write as 13 over 13 plus 12 over 13. And 13 plus 12 being 25 over a common denominator of 13. So this gives us 25 over 26. All right, now the question asks us to find sine, and we found sine squared. So we just need to take the square roots. Okay, Let's choose whether we need to plus or minus here. Again, whenever we're the ones introducing a square root en route to solving a problem, we need that plus or minus until we can decide which one actually to choose. And we were told that theta's in quadrant 3, so therefore sine of theta is negative. So we're going to go with the negative there. And distributing the radical into the quotient, we have the square root of 25, which is 5, over the square root of 26. But this needs to be rationalized, of course. So here we're going to get our final answer. Negative 5 rad 26 over 26. Okay, for our last example, let's verify this identity. And yeah, we've verified a bunch of identities so far. So same strategy as always. We should start with the side that is either more complex and or has a clear directive on what to do with it. And if you think really hard about this one, you may come to the conclusion that the left side is slightly more complex than the right side. So that's what I feel like, and I say we start with the left side. So we will start by writing down the left-hand side. And again, at no point are we going to say this is equal to cotangent of x. That is simply not allowed. It's a fallacy in math, very subtle. It's called begging the question, where essentially you're using the conclusion in its own proof. All right, so we do have a clear directive here. We have two double angle trigonometric functions, so we ought to just break them open using their double angle identities. So let's just pick on the standard cosine one out of the main three. So cosine of 2x, let's write that as cosine squared of x minus sine squared of x. And in the denominator, sine of 2x, let's write that as 2 sine of x cosine of x. Okay, so yeah, well, looking at the numerator, we have a 1 minus sine squared. So that is indeed cosine squared. So what we have is cosine squared plus cosine squared is equal to 2 sine x cosine x. Okay, well that's just 2 cosine squared in the numerator over 2 sine x cosine x. And we can cancel a factor of 2, but there's more. We can also cancel a factor of cosine. So the one factor of cosine canceling from the numerator and a factor of cosine canceling from the denominator will give us simply cosine of x over sine of x. Yeah, this seems like a good time to look at the original problem and think about what we're trying to get, which is just cotangent of x. Oh, excellent. Cosine over sine is that. So just write it as cotangent of x, and that is indeed the right-hand side. So we have proved this identity.